Assalamualaikum warahmatullahi wabarakatuh. Okay, bertemu kembali. Okay, we are going to learn about waves. Okay, so waves is the last part in chapter 7. Okay, so we start with the word waves. The study of wave is very important in physics because many physical phenomena such as interference, refraction, okay, you can see here, reflection and polarization are based on the principle of wave motion. All forms of waves are associated with the transport of energy. Okay, let us go to the example of waves. Okay, water wave, for example, and then electromagnetic wave. And then another example is seismic wave, which caused the earthquake. Okay, that is the example of wave. And then sound wave. Okay, that is the example of wave. Okay, let us see here the types of wave. We go to the types of wave. Okay, there are two types of wave here. One we call it, okay, so this is the important point here that you should know. Type of waves. Okay, there are two types of wave. One we call it transverse wave. Transverse wave, and another one is longitudinal wave. Okay, transverse and longitudinal wave. You should be able to differentiate between transverse wave and longitudinal wave. Now have a look at the definition of transverse wave. Okay, the transverse wave is a wave that propagates in a direction perpendicular to the direction of motion of the wave. For example, is light wave. Okay, go to transverse wave first. Okay, transverse wave. Okay, this is this is the particle. Okay, particle. This is the particle. You can see here. This is the particle. Okay, particle in a medium. Okay, and this is the direction. For example, this is the direction of propagation of wave. Okay, look at here. Okay, this is the particle. The particle in a medium will vibrate up and down. You can see, look at the sketch, look at to my sketch here. The particle move up and down, up and down. This is the movement of particle in the medium. Okay, so the direction, okay, look at here. A wave that propagates in a direction perpendicular to the direction of motion of wave. Okay, so this is, for example here, this is the direction of propagation of wave. Okay, so this is the movement of particle in a medium. So the movement of the particle in the medium, okay, or the vibration of the particle in a medium is always perpendicular with the direction of the propagation of wave. Okay, that means here the movement of the particle here is up and down, up and down, up and down. Okay, that means the movement of the particle in my sketch here is vertically, and the propagation of wave is horizontally. So the propagation of the wave and the movement of particle is perpendicular. That is transverse wave. So the example of transverse wave is light wave, which is electromagnetic wave. Okay. Now we go to the longitudinal wave. Okay, longitudinal wave. Okay, so this is the particle. Let me draw the particle first. Okay, the particle in the medium. This particle move, the vibration of the particle is left to right, left to right. This is the vibration of the particle. For example, this is the direction of propagation of wave. Okay, so this one is the direction of propagation of wave, this one. Okay, the direction of propagation of wave. Okay, the direction of the propagation of wave is to the right. And the particle, look at here, the particle move, every particles in the medium move left to right, vibrate left to right, left to right. Okay, so look at the definition here. Have a look at the definition here. A wave that propagates in the direction parallel to the direction of motion. So the vibration here is parallel with the direction of propagation of wave. That is longitudinal wave. And the simple example of the longitudinal wave is sound wave. Okay, this is the example of transverse wave, this one, this figure. And this is, you can see here, we can see here, what we call here, look at the form of the wave here. Okay, the form of the wave is like sinusoidal graph. Okay, so here you can see the movement, okay, of the spring here. Okay, when someone move it up and down, look at the form of wave. This is the example of transverse wave. Okay, figure 7.7b. Okay, someone, okay, hold at the end of the spring, and then another one hold at the end here. Okay, and this person, okay, move the spring back and forth, so you can see here rarefaction. You can see the rarefaction. This is the rarefaction, and this part, okay, this is rarefaction, this part is compression, and it is repeated. Okay, so this is what we call longitudinal wave. So you imagine someone hold the spring. For in your secondary school, okay, if you experience doing the experiment about spring slinky. Okay, remember spring slinky. It's a long, very long spring. Someone will hold at both, not someone, there are two person will hold, okay, hold at the end of the two ends. Okay, so the motion of the spring is up and down. One person will move it up and down, and then for the second experiment, that person move it back and forth, and you can see the form of the wave, the form of the spring. So it illustrates the longitudinal and transverse wave. Okay, so properties of wave. Okay, so look at this one. Okay, this is the illustration of wave. Okay, you can see here, look at the figure 7.8. In figure 7.8, okay, the wave can be illustrated by using sine graph or cosine graph. So here the label of axis here is y versus x. Y is the maximum, the displacement, the vertical displacement, where x here is the propagation of wave. Okay, So if you calculate from this point to this point, here we call it wavelength. Okay, so from zero here, zero, okay, to this point here we call it amplitude. Okay, so one complete oscillation is this one. This is one complete oscillation. So you can calculate the wavelength. You can calculate it. Start from, okay, sorry. Okay, you can calculate, start from here to this part. This is also the wavelength, or from crest to crest, or trough to trough. This is the wavelength. Okay, so definition of the amplitude. Okay, this is the amplitude. You can see here. Okay, the maximum displacement from the equilibrium position, that is the amplitude. And then the wavelength. What is the wavelength? The wavelength is the linear distance between two successive particles of the medium that are vibrating in phase, or the distance over which the wave repeats itself. Okay, and then a definition of displacement y. Okay, y. So y is, okay, it can be at this point, okay. What is the value of y here? Okay, for example, at this point, what is the value of y here? Okay, y here is the distance of a particle in a medium in a certain direction from its equilibrium position. Okay, and then definition of f, you learned it before. F is the frequency, or the number of oscillation made in 1 second. That is the frequency. And then about the period is still the same. The definition of period, the time taken to complete one oscillation. And then here you also learn, okay, the wave propagates either to the left, to the right, up, or down. So from here, when there is a propagation of wave, okay, there is a velocity. Okay, so the velocity of wave is equal to f lambda. This is the equation for the velocity of wave. Okay, where the unit is in meter per second. Velocity of wave. The velocity of wave is the product of frequency and the wavelength. Okay, and then there is the definition of wave number. Okay, wave number. Let us see the general equation. I show you the general equation for the wave first. Okay, this is the general equation. Okay, look at this part. Okay, y, okay, I write the equation first. Y is equal to okay, y x t. That means y as a function of x and y as a function of t is equal to a sine, okay, kx plus minus omega t, and then plus minus v. Okay, look at this part. This part is similar in simple harmonic motion, but in simple harmonic motion there is no kx, because in simple harmonic motion that is a static vibration. There is no propagation. In simple harmonic motion there is no propagation of wave, so there is no kx here. So what is meant by kx? Okay, I will explain to you after this. Okay, so back to, okay, you can see. Okay, let me draw first the form of wave. Okay, so this is the example. Okay, for example, this is the wave. My drawing is not good. Okay, I'm sorry. Okay, so you can see here. Okay. Okay, look at this part. This is the propagation of wave. Okay, propagation of wave. That means the wave move to the right. Okay, this is X, this is Y. Okay. Alright. So from here, okay, by seeing this general equation, okay, and the graph here, okay, okay, look at here, A is the amplitude. So y is the displacement from the equilibrium position. So this is y, this is x, y is the displacement from the equilibrium position. Okay, that is y. Okay, and then A is from, okay, is the maximum displacement from the equilibrium position. This is A. And then sine, okay, sine kx plus minus omega t plus minus phi. So phi here is the phase constant, okay, and then omega is the angular frequency, and then t, okay, t is at any time, okay, and then kx, k here is, we call it wave number, okay. K shows the direction of wave. If there is a propagation of wave, so there is wave number which shows the propagation of wave. Okay, so in simple harmonic motion there is no propagation. That's why there is no kx in the equation. Okay, so here look at this part. We consider the wave that form in a string as shown in figure 7.11. If the wave moves to the right, the equation of wave becomes minus. Okay, minus. Okay, so you can write the equation y is equal to a sine kx minus. So when you see the minus sign here, it means that it moved to the right. Okay, when you see the plus sign here, that means the wave moved to the left. That is the direction of wave. Okay, plus and minus shows the direction of the wave, whether to the right or to the left. Okay. Okay, back to this one, back to this part. Okay, that is the wave number. So you can read the definition of the wave number here, and then the angular frequency and phase difference. So this is, we call it phase difference, this part. Okay, this part is the phase difference. Okay, the phase difference between 2 points separated by the distance x is given by 2 pi. Okay, this is the equation. Phase difference is equal to 2 pi x over lambda. Okay, so have a look at the example here. Example 7.7. A sinusoidal wave traveling in the right, okay, direction has a frequency of 10 Hz and wave velocity 20 meter per second. Okay, question A. Look at A. Compute the angular frequency. So you are given F is equal to 10 Hz, and then the wave velocity V is equal to 20 meter per second. Okay, A, compute the angular frequency. So it's simple. Angular frequency is equal to 2 pi F. So this one, 2 pi times 10. So you will get 20 pi radian per second. Okay, that is about angular frequency. And then B, compute the wavelength. Okay, how you are going to calculate the wavelength? Okay, now you are given the value of wave velocity. So V, don't forget this equation, V is equal to F lambda. This is the equation of wave velocity. So from here you can get lambda, where lambda is the wavelength. So V divided by F. So V here is 20 divided by 10. So the wavelength is equal to 2 meters. Okay, and then C, compute the wave number. Okay, C, the wave number. Okay, here. Okay, you can use this equation. Okay, the equation for wave number is K is equal to 2 pi over lambda. So here 2 pi divided by 2 meter. So is equal to pi, okay, meter minus 1. That is the unit for what we call the wave number, meter minus 1, or sometimes cm minus 1, or sometimes mm minus 1. So this is the equation of wave number, and then here is the equation of, this is wave velocity, this is wave number, and then here is the equation for the angular frequency. Okay, look at this one. Look at this one. This is, we call it displacement distance graph. Displacement is y, distance is x axis. Okay, displacement distance graph. So from here we can know that from this figure, okay, from this figure we know that the amplitude, okay, of the wave is 0.75. So this is the amplitude. The wavelength, distance for one complete oscillation, okay, you can calculate the wavelength start from here to here. Okay, so this is one complete oscillation. So therefore you can calculate the wavelength. The wavelength is 0.5 meter. Okay, all right. So this in chapter wave, there are two types of graph. One, we call it the displacement distance graph, and then second is the displacement time graph. So there are two. One is y versus x. So y versus x is displacement distance graph. Okay, and another one is y versus t. Okay, so this is the displacement time graph. Okay, the displacement time graph shows how the displacement of the particles varies with time as shown in figure 7.10. So you can, from the displacement time graph, you can calculate the period of oscillation. So from here to here, this is t. Okay, so t here is equal to 0.1. You also can get the amplitude, the value of amplitude from the displacement time graph. So this is the amplitude. It's similar like above. The amplitude is 0.75. Okay. So t here is in second. So t for this figure, t is equal to 0.10 second, which means 0.10 is the period of oscillation. Okay, let us see the example of 7.8. Okay, a sinusoidal wave has a frequency of 25 Hz. So you are given for example 7.8, the frequency is equal to 25 Hz. And the wave velocity, you are given the wave velocity is 20 meter per second. If 2 point in the wave phase difference is 30, okay, compute the distance between the points. Okay, you are given that the phase difference, okay, phase difference is equal to 30 degree. So you have to convert it to radian. So here when you convert to radian, it becomes okay. I can't remember the conversion. Okay, wait. Okay, so 180 is equal to pi radian. Okay, so here 1 degree is equal to pi over 180. So therefore 30 degree, 30 times pi divided by 180. So from here you will get 30 times pi divided by 180. So from here you will get 0.52. Okay, so 0.52 radian. So this value, okay, 0.52 radian. So you are given the frequency, wave velocity and the phase difference. Compute the distance between the points. The distance between the points, that means you have to find x distance. Okay, so distance, okay, remember the equation of phase difference is equal to 2 pi, okay, 2 pi x divided by lambda. X divided by lambda. Now we know the we know the value of phase difference. Okay, but we don't know, we want to find x, but we don't know the value of the wavelength. So the wavelength can be determined by using V is equal to F lambda. So lambda is equal to V divided by F. So V here is equal to, so look at V is 20 divided by 25. So from here you can get 20 divided by 25 is equal to 0.8. So 0.8 meter. So therefore, okay, X is equal to 5 lambda divided by 2 pi. So here the phase difference is 0.52 times 0.8 divided by 2 pi. So from here you can get 0.52 times 0.8 divided by 2 pi. Okay, the answer is 0.067. 0.067 meter. Okay, this is the way how you're going to use this equation, the phase difference equation. Okay, so x here is the distance between the points. Okay, distance is the distance between the point. Okay, let us see example 7.9. Okay, example 7.9. You are given the equation y is equal to 8 sine 30t plus 40x. So from here you can see here, from here we know that the wave propagate to the left because plus sign. Okay, so 8 here is the amplitude. Okay, this is the angular frequency, and then here is k, x, the wave number. Okay, let us see the question. A, compute the frequency and the wavelength of the wave. So the frequency, you can find the frequency from omega is equal to 2 pi f. So f here is equal to omega divided by 2 pi. So omega here is 30 divided by 2 pi. Okay, so when you calculate, you will get 4.78 hertz. This is the unit for frequency. And then you are asked to find the wavelength. So the wavelength can be determined from k. So k is equal to 2 pi over lambda. So the wavelength is equal to 2 pi over k. So 2 pi divided by k here is 40. So k divided by 40, 2 pi divided by 40 is equal to 0.16 meter. Okay. And then compute the displacement of the wave. The displacement of the wave when x is equal to 4 cm and t is equal to 0.1. Okay. So when you want to calculate the displacement, okay, according to this equation, 8 sine 30t plus 40x. Okay, so this is the displacement. Just substitute the value of x with 4 cm. Okay, convert it to meter, and then t with 0.1. So 8 sine 30 0.1 plus 40 times x 0.04. Okay, so don't forget to change the mode of your calculator from degree to radian. So when you calculate, you will get minus okay, let us calculate it back. Okay, let us see. Okay, 8 times this is radian. Okay, 8 times sine. Okay, so here is 30 then 0.1 plus 40, and then here is 0.04. Okay, so the answer is, let me see, 0.1. Okay, look at here. This is 4. Okay, you have to change it. They forgot to change. Okay, look at the example here. Okay, the problem here is, okay, this is the unit here is cm, so you have to convert it, becomes 0.04. so here you should put 0.04. so when you calculate, you will get negative 7.95 meter. So this is wrong. This is wrong. The example, the solution here is wrong. Okay, this is the way how you are going to use the equation, okay, when you are given the equation of displacement. Okay, so we stop here. Okay, your syllabus is until here. Okay, thank you for watching. I try to do the tutorial, okay, and we will discuss about it. Okay, assalamualaikum warahmatullahi wabarakatuh.